Hi folks, we're going to take a look at question 35 from section 9.3. So what we have here is essentially an initial value problem. We have a differential equation, that is an equation whose solution is a function and contains derivatives, and we're given an initial value. We know that y at 0 is equal to 2. Now, the first question they ask is, can y be represented without using an integral? And hopefully we recognize now that e to the minus x squared is a function that is not easily integrable, and so the answer for A would actually just be no. Now, since representing the function as an integral is the only thing we know how to do, I think we'll write it out anyways, because that might actually help us solve the rest of the problem. Now, before I go on, I will mention that this is a very important question for those of you who are going to be studying engineering, because I'd mentioned earlier that we would see another way to deal with differential equations, in particular differential equation that we can't just solve easily by integrating a function. So we'll see how that works in a little bit. So let's recall how we could give a solution to this differential equation, okay, as we actually wrote the answer in integral form. So we took the integral with x being our upper limit of integration of this function here. Since we're using x as the upper limit of integration, we can't use it as the variable of integration, so I'll use t instead. So the integral of e to the minus t squared dt, and what we used as our lower limit of integration was the x value of the given point, okay? And then we needed to add a constant, which was always the y value of the given point. Okay, so that when y is equal to 0, you have the integral from 0 to 0, which of course is just 0, then plus 2, which gives you the initial value that you're given. Okay, what we want to do now in part B is they're suggesting that we might be able to write the solution using a power series. And this is that method that I was talking about, another way to deal with differential equations. And that's by representing the functions by their power series. So let's just recall here on the side that the power series for e to the x is just a sum from I equals 0 to infinity of x to the I over I factorial. Okay, so we can easily now determine the power series for e to the minus x squared. We just have to replace x now by negative x squared. So I goes from 0 to infinity of negative x squared to the I over I factorial. And let's just write this in power series form. So we have I from 0 to infinity. So we'll have to extract that negative 1. So we have negative 1 to the I, and this just becomes x to the 2I over I factorial. And this is now the function that we're going to integrate to come up with a solution that doesn't involve an integral. Okay, so let's do that here. So we're going to take the integral from 0 to x. Instead of e to the minus t squared, we're going to use the power series expansion. So we've got the sum I equals 0 to infinity of negative 1 to the I, x to the 2I. Oh, let's be careful here. This really should be t, since we can't reuse x as our variable of integration over I factorial. Okay, dt. And again, we use the property that the integral of a sum is the sum of the integrals, which we also assume to work for infinite series. So what we can do is integrate term by term. So I equals 0 to infinity, and the integral from 0 to x of negative 1 to the I, t to the 2I over I factorial dt. Now, of course, let's not forget, as I did here, that we need the plus 2, as we need this to still satisfy our initial condition. So here, we'll just make sure we incorporate the plus 2. Okay, now this is an easy integral to take. And again, why we use this trick for representing functions with their power series is that power series are always easy to differentiate, and in this case here, easy to integrate. So that's why they work well with differential equations. So let's just finish this off. I equals 0 to infinity. So let's take the antiderivative here. The negative 1 to the I and the I factorial act as constants within this integral. So we just have t to the 2I plus 1 over 2I plus 1, evaluated from 0 to x. And let's not forget the plus 2. And so here we can see that when we evaluate the integral, the second part will just go to 0. So we have sum I equals 0 to infinity of -1 to the I, and here we'll have x to the 2I plus 1 over I factorial times 2I plus 1. Okay, and then plus 2. So what we've managed to do here is to find a solution to this differential equation that does not involve integrals, something we were not able to do earlier on. Okay, so there we have it, part B. Now in part C, they ask us for what values of x do we expect this to converge. Well, let's go back to what we started with. We had e to the x, which even though we haven't showed it yet, they tell us that the power series for e to the x converges for all x values. And of course, we've already shown that the series converges to the function itself. So here, when we put in negative x squared, that won't change the interval of convergence. This should still converge for all x values. And we saw in one of our theorems, the one that followed the definition of a power series, we saw that when we integrate a power series, that new function will keep the same interval of convergence. Okay, so we can say that this converges on all real numbers. Okay, and that comes from the fact that e to the minus x squared converges on all real numbers, which comes from the fact that e to the x converges on all real numbers. And that's our justification. Okay, thanks.